Hey, hi everyone. Good evening. Welcome back. We are going to discuss about the geospatial analytics. Of course, we are still talking about geospatial analytics itself. And as part of today's session, we will be discussing about how clustering can be used or implemented on geospatial analytics or geospatial or GIS data. Before that, we need to understand what is the clustering, right? We need to understand what exactly is clustering in the first place. Now, as part of the analytics, clustering is part of data mining unsupervised learning technique. Data mining unsupervised learning technique. This unsupervised learning techniques are specifically used for performing descriptive analytics. This basically means that in our historical data, we don't have label. So I'll say no label. All right, so that is the point that we need to remember. That means in our data set, in generic scenarios in our data set, we don't have an output variable y. This is not there. Right? This is called as your label, and we don't have that. So that means whenever we are trying to develop something with respect to this data set, we are not focusing on identifying or referring to the label. All the data points are considered together. And then we'll try to extract information from all these columns from, right, for all these data points that we have. So we have records, rows, right? And the information about each record that we speak about is obtained by these columns. And we are taking all these columns to understand the characteristics of each row. And then we try to group the data based on their similarities. Clustering is about identifying the similarities. Now, any data set that, any analytics we speak about is all about identifying the pattern in the data, some specific pattern, which is hidden deep in the data. We need to identify that. And once the pattern is identified, you'll also be able to identify the deviation. So you're expecting something, but it may not happen. Now you need to understand why the deviation is happening, what is causing the deviation, and what is the impact of the deviation, right? So when you try to investigate on these deviations, you'll be able to understand the answers for that deviation. That is nothing but your analytics. Understand the pattern. And once you are able to understand the pattern, understand the deviations as well. And once you're able to figure out the deviations, you'll also be able to understand why those deviations are coming. Now here, in unsupervised learning technique, that is your clustering, also known as segmentation, we are trying to understand how we can reduce this variation in the data. So if I have a very large data set, there may be a lot of different characteristics for each row. So we are going to capture those variations in the data. Now, if I try and identify the records which are similar to each other, and then I can probably try and group them. For example, here I will have a group. All the records which have these characteristics, right? Specific characteristics, I'm putting them here. Then similarly, I'll have another group. I'll put that in blue color. So these will have different characteristics. So if I basically try to find out like this, maybe these blue lines, right? They are all of similar records. Then we have pink lines, and then we also have yellow records. So you can see my data might have combination of all these different records. Variations are there, but all of them are combined. So when I look at in this, right, in this case, if I look at the data set, I see a lot of uncertainty. In order to make any decision, it becomes too difficult for us to make that decisions because you have a lot of variations in the data. Now, when you look at this particular data set, you see that the data has some kind of homogeneity. So all the similar records belong here, all similar records, right? Pink records, red, blue records here. This is called as homogeneity. That means you will be able to understand what characteristics that these data points have, what characteristics that these data points have, and what characteristics that these data points have. So in order to make certain decisions or descriptions, or if you want to analyze this data, it becomes easier in this case after you group the data, right? So clustering is basically trying to segregate the data based on their similarities. And when we talk about this clustering, the clustering is implemented using distance logic. So cluster analysis is basically performed at the initial stage itself, initial stage of your analysis. We are looking at the variations in the data. So we call it as an exploratory method. This is probably one of the first steps that we do on the data. The clustering is basically a process of identifying similar group of records. Homogeneity means similarity. Then the idea here is to bring up similar items into one group. And if I try to group that, right, so we try to do that. If I go back to the diagram, this one. Within this particular record, within this particular data set, the records will be similar. I do not see any data point which is pink in this yellow group or in this blue group. So we will have the homogeneity. All the yellow records belong here. All the pink records will belong here. All the blue records will be belong here. Within a group, we always need to have more similarity. So if I have something like this, then this is not a good grouping because you have a different record altogether. Right? So that is the objective of clustering. And in order to quantify this, implement this, we use distance measure. Similarity is a qualitative measure. Whereas in order to quantify that similarity, we use distance techniques. Now, whenever we talk about distance, right, it is measurable entity. So if I have two data points, point A, point B, in an X and Y plane, if I have to draw these data points, then I will be representing this as X1, Y1, this as X2, Y2. Right? X1, Y1, X2, Y2. Now, this is two data points and this is the distance. Now, how do I measure the distance between these two data points? Here we have the distance measure from your trigonometry. You can talk about the Pythagoras theorem, right? So it talks about a square plus b square is equals to c square logic. Using that, we will try to identify the distance logic, distance formula. It is also called as Euclidean distance method, right? Euclidean distance. So A is represented as x1, y1. B is represented as x2, y2. So on x-axis, these two data points are at a distance of x2 minus x1. On y-axis, we have the distance between them as y2 minus y1. But when I do these calculations, the data points might be here, B could be there, or B could be here. So if I say this, my y2 might be here in this case. So what is happening is the distance that you're drawing is going to become a negative value in that case. So positive and negative, the distance gets impacted. Now you may get also zero value. That means there is no distance at all. But ideally, it is the negative value, right? Negative calculation, which is impacting this entire summation that we are doing. Now to overcome this negative symbol logic, we do squaring of the values. We are squaring these numbers. Now, when we do the square, we get magnitude. Right? We are trying to eliminate the negative symbol. We'll get magnitude of the distances between these 2 points. But because we are squaring, you also want to bring back the original value by doing the square root of the entire value. The summation of after you do the calculation, you might want to do the square root. This is called as Euclidean distance. And this is how we measure the similarity. So if I bring in another data point called C, right, A, B, C, 3 data points, we can clearly say that A and C are more similar. Because if I draw x3 here and y3 here, we can clearly see that x1 is close to x3 rather than x2. So the difference between them is less. Similarly, from y1 to y3, the distance is less. When the distances are less, you can clearly say that the characteristics of the data might be similar. Right? So from that perspective, distance is used to quantify the similarities. And clustering is all about capturing that distance between the data points. And it has to be in a multivariate space. What we are looking at is an example from a two-dimensional space, right? I've just shown you the two-dimensionality calculation, but we need to look at multi-dimensionality. So Euclidean distance is extended to multiple dimensions. Now, whenever we're doing the clustering, we also need to remember that the records that we have, we're grouping them together, right? The idea is to ensure that similar records belong to the same group. This also means that dissimilar records should not belong to that. They should belong to a different group altogether. Again, if I go back to the drawing, if I erase all this, you can see the colors here, right? So if you look at the 3 boxes here, yellow, blue, and pink. Within yellow, you should have all yellow records. Within pink, all pink. Within blue, all blue records. So that is your homogeneity or homogeneous. The second point that we are also talking about here is the heterogeneity. That means within the yellow cluster or yellow group, we are saying that you should not have either blue one or pink one here. Dissimilar items, they should be placed in a different group altogether. Right? So these 2 points are complementing each other. Right? If you are trying to put all the similar items in single group, then obviously dissimilar records will not fall in that group, right? So these are the 2 important points, which of course complement each other, that we need to create or obtain when you are doing the clustering exercise. Right? You can see that. So all the similar records, red one, now we are having blue one, and then we are having the green one. right? So this is how the clustering needs to be performed. Now, when you have a single value, you can directly group the data, split the data and say that, hey, from here to here, this is group 1, here to here, group 2, here to here, group 3, or whatever the groups are. For example, this is 0. Probably this is 15 years. I will say young, right? Or maybe I'll say 12 here. And from here to here, I will say teens. From probably 20 to 30 years, I'll probably talk about, or maybe 40 years, I'll talk about middle age group, or 50 maybe. And then if I talk about 100, then this is old age. So this way I can categorize, right? Group the data if I have a single variable. Even if you have two variables, then it is very easy because we can visually see the data and then try and say that, hey, this is one group and this is another group. But the problem will arise when we have more than two variables, because we cannot visualize the data, right? And this is where we need to quantify. And that's where we use distance techniques. And in order to measure the distances and group the data, we use broadly two approaches. One approach is by naturally arranging the data in specific order based on their distances to create hierarchy. Once we create the hierarchy, we basically try and group the records. But first we have to create the hierarchy. This approach is called as hierarchical clustering, or we can also call it specifically in hierarchical clustering. One of the approach that we are going to do is agglomerative clustering. Whereas the alternative approach that we have, which is also known as non-hierarchical approach, will not look at creating any hierarchy. There's nothing like natural grouping here, but we try to group the data randomly and then try to improve within group similarities by elimination process. So I'll try and group all the, let's say, students together, and I'll see exceptional students. When I find exceptional students, I'll remove that from the group, right? Probably I'll have to assign them into an appropriate group into which they fall in. For example, these students are very high performing students. Then I would remove the student from this group and put that student into a high performance group, right? High performing students group. When I do that, the first group is automatically getting a better homogeneity. The similarity is automatically increasing. Right? So that is about your second approach. This is called as hierarchical approach. The second one is called as non-hierarchical approach. In both the cases, we are basically trying to do the distance calibrations. Now, there are different approaches within the hierarchical clustering also. Here we are calling them as agglomerative or divisive. We specifically talk about agglomerative clustering. The agglomerative clustering will allow us to start with n records, right? If I have data points, let's say these are all different data points that I have. So I will call them as n records, n rows. So in agglomerative clustering approach, which is the default clustering that we try to do, we will assume that each record is a group in itself. That's the first assumption that we make. And then we'll try to group the records together. Right? And then we will try and measure the similarity between the records. We do pairwise similarities. Now, what does this pairwise similarity actually mean? So let us try and look into this example. Let's assume that these are my records. I'm calling records as A, B, C, D, E, F. Okay, assume 5 records are there. I'm plotting these records here. So to start with, we have 6 clusters. Okay, we're assuming that we have 6 clusters. Each record is assumed to be a cluster in itself. Then we are going to find all the distances between the records. That means we are trying to create pairwise record distances. So that means A to B, A to C, A to D, A to E, A to F. But we also have to look at B to C distances, B to D, B to E, B to F. Similarly, we'll try and do distance between C to D, C to E, C to F. Then E to D, D to E, D to F, and finally E to F. So we are creating pairwise distances. We're calculating all the pairs. So like this, I'll measure all the distances, right? And once the distances pairwise are calculated, we will know which of these pairs are closely placed. Which of these records are close to each other. Let us assume that this pair and this pair are the most closest. Assume. So what should we do? We merge these 2 records. And now we are calling this as your cluster. So now I have only 4 clusters. From 6 clusters, it has become 4 clusters. Now again, we will try and look at the distances between these pairs, A to BC, A to DE, A to F, BC to DE, BC to F, and then finally DE to F. Right, so we are trying to create the distances here. And once again, we will repeat and understand which pair is closest. When I look at the distances, we probably have found that DE and F pair are the closest, maybe, just like this. So we are going to now merge DE and F. So this becomes 1 cluster. So we are left out with 3 clusters now. Then what we do? We again repeat the process A to BC, A to DEF, and BC to DEF. Right? So this way we will try to measure the distances. Again, we will merge, and we found that now we have only 2 clusters. So here these are merged together, BC and DEF are merged together. So I'm going to have only 2 clusters. And ultimately these 2 are right combined together and we get a single cluster. So the agglomerative clustering approach that we speak about is a process of merging the similarities, right? Or similar pair of records. We keep merging them. Starting with 6 clusters, we end up getting to 1 cluster. Exactly opposite approach is called as divisive approach. Here we are trying to divide. Right? Agglomerative is merging based, divisive is dividing based, or splitting based, or separation based. Now, once I have this hierarchy created, right, the flow is created, then we will be able to understand how do we cluster the data. This visual representation, the tree-like diagram that you're looking at, this is called as Dendrogram. This is a flow diagram kind of a visualization. We are trying to have a specific flow from 6 clusters to 1 cluster. Now, once we look at the dendrogram, we will be able to come up with the logic on how do the clustering can be implemented, or what records should belong to what cluster and all that. So step 0 to step 4, this is agglomerative. Step 4 to step 0, this is divisive approach. Agglomerative, divisive. Right, we call it as Agnes, and this is Diana. All right, next. There are various other techniques also, like brick approach, cure approach, chameleon approach. All these basically will have your hierarchical approach only. Brick stands for balanced iterative reducing and clustering using hierarchies. Cure means clustering using representatives. Chameleon is chameleon itself. It's explained as chameleon itself. Based on the similarities that we try to measure. Now, when we talk about distances, the formula that we have used is Euclidean distance formula. Okay, and before when we proceed doing the formula, doing the calculations, we need to understand certain things with respect to distances. These are the properties that you need to remember. A distance is a physical entity, and it will always be positive. It has to be greater than 0. It cannot be negative. The distance cannot be negative. And distance from itself, right? If I have a point called I, distance from itself is equals to 0. There is no physical movement. So it becomes 0. And distance is always symmetric. So from point A to B, if I have distance 5 meters, then B to A is also 5 meters only, right? It doesn't change. We're talking about shortest distance possible between two data points. So it will be symmetric. And then we also have triangle inequality. This is if I have I and if I have, let's say, K. We're talking about distance between IK. So D of I and K will be equal to, if I put a data point called J on this shortest path, then this can be explained as IJ plus JK. Right? So the total distance is nothing but distance between these two and these two. This holds good when the data point is falling on the shortest distance between I and K. What if J is here? Then the distance that you are going to draw, like this, where you say dij plus djk will always be greater than dik. Right? If you try and merge this, it will come here. This will come here. So this point will be extra, right? Additionally, you are getting twice. Isn't it? So this is called as triangle inequality. Some of the basic properties that we need to remember with respect to distance calculations. Now, whenever we want to calculate the distance between the records, then we will try and use this formula. This is called as Euclidean distance measure. But we don't stick to this. This is one of the approach. Of course, this is the default approach that we use for distance measure. But we can also use various other distance metrics that are mathematically possible. So you can see there are different formulas that can be used. Couple of examples are given here. Manhattan distance, statistical distance, that is Mahalanobis distance. So these are other examples that we can probably look at. Now, this is all possible when you have, these formulas can be used when your data is numeric, continuous. If the data is categorical and binary, then we can only do comparison. And when we do the comparison, you can see these are the data points that we are trying to take into consideration. We have 3 records: record A, record B, record C. Right? So we have 3 records here. And these 3 rows has 3 columns. And within this data points, column 1, column 2, column 3, x1, x2, x3, the values that we have is binary value. So data is only binary. So in this case, if I have to measure the similarity between the rows, A and B, or A and C, or B and C, then we can only do the comparison. We cannot do arithmetic difference calculation. Right? We cannot do a subtraction. Right? So when we talk about all these comparisons, right, 2 by 2 table of counts, when we talk about 2 by 2 data, we are going to right, see how these records are similar. For example, I want to measure the similarity between A and C. Okay. So if it is A and C, then if I talk about A being a graduate, is C graduate? No, right? C is not graduate. So with respect to graduate feature, that is X1, these 2 records are different. With respect to alcoholic feature, again, they are different. And with respect to X3, this is vice president, we can see that they are similar. So the similarity can be measured as 1 out of 3. Or dissimilarity can be measured as 2 out of 3. Right? This is similarity. This is dissimilarity. Right? Now, this can be done by coming up with a cross table. Or you can say pivot table, summary table. A can have values either yes or no. There are the only 2 options that A can take. So I'm going to mark those values here for A. Similarly, C can take only 2 options, either yes or no. So I'm marking those values here. Now I'm going to count the number of instances where A and C are having similar values or same values or dissimilar values. So in how many instances in these 2 records, in how many instances both A and C are having values as n? If you observe, A does not have even a single right value which is n. It's not repeating at least once. So you're going to mark that as 0 here. Similarly, with respect to the value where A is n and C is yes, if we try to find out, that will also be 0 because A does not have even once the value n. Now, if I talk about the A value being yes and C value being n. So I have 2 instances. So I'm recording that 2 there. And finally, I'm going to look at A being yes and Y also being yes. So we are having 1 instance. right? So this is your cross table. Now, using these values as a reference, we can create the same similarity and dissimilarity measures. We can come up with similarity and dissimilarity measures. I'm replacing these values with A, B, C, D as a positional variables to represent those values. And if you observe A and D, which are in the diagonal, these values are giving us a measure of similarity between A and C. These two values are similar. So what is the similarity between A and C? Diagonal values is 1 by total. Total is 3. This is exactly we tried to measure, right? Similarity is only one case out of 3. Mathematically, this is measured like this, and it is called as simple matching coefficient formula. Right? So this is giving us similarity. On the same lines, if you try and measure the dissimilarities, when I say dissimilarities, we are trying to look at C and B, B or B and C, where one value is no, the other value is yes. Right? So one is yes, the other one is no. This is dissimilarity. Now, how many values we have here? Dissimilarity. If I map this, then we have 2 by 3. Now, this is mathematically represented as B plus C by total. This is your dissimilarity. We also have different formulas. This one of the formulas is called as Jaccard's index. In Jaccard's index, we are not considering this case, right? A is not even considered in the formula. So the logic says that if I know that, right, if you have the value that A is not a graduate and C is also not graduate, for example, these two are no's and no's, or if I talk about B and C, for example, here you see no and no. If there are no values, right, if both of them are no, then how can you conclude whether they are similar or dissimilar? You may seem that they are similar, right? But one could be undergraduate, the other could be postgraduate. Just because they are not graduate does not mean they are same. Isn't it? So that is the similarity measure. We are simply ignoring that value because we have lack of information. Right? So that is how we measure the Jaccard's index. So this is a different formula. I mean, these are the different formulas that we use for measuring the similarity aspect between data points if your data contains non-numeric values. Even if that means your data is not having binary, it has more than 2 values, more than 2 options. In our discussion till now, it is only yes or no. But what if I have more than 2 options? Right? So in this case, we would basically talk about the distance being either 1 or 0, based on the similarities in the categories. So if both the data points, right, if both the records belong to same category, then we are going to say that there is no distance. That means they are similar. That's the interpretation. Distance equals to 0 means they both are similar. Whereas if you talk about 1, when the records belong to different categories, right, when they are different from each other, that's when we have 1 here. right? So that is basically how we try and look into the distances if your data is non-numeric. There are various other cases also. For example, what if your data is mixed data? Right? You might have combination, non-numeric data and numeric data. So in such cases, of course, we will have to convert everything into numeric case and then do the distances calculations. Right? So you'll use these non-numeric logic onto your non-numeric data. Right? You can split your data into numeric categories and non-numeric categories, non-numeric columns. And numeric fields can be right, simply used using the calculations that we discussed. We measure the distances there. And non-numeric data, we can use this logic and then try and map all the distances. Ultimately, we are going to get something like this. This is called as dendrogram. And using the dendrogram, we will split or we will group the records. For example, if I flip this, right, it is easy for us to understand if I flip this entire visualization here. So I'll start with A, B, C, D, E, F. A, B, C, D, E, F. And we said that to start with, B and C have been merged together and we have a record. So I have A, B, C. Then here also we merged DE and I have EF. Right? So I'll mark this as 0. Then we said these two are merged together and here we have A, B, C and DEF. Then we merged these two together and we have A and DEF. And finally we merge this like this. It's a flow diagram, right? So this representation is called as dendrogram. So if I have to understand, right, this graph, so let us again remove this. So what we are doing is we are trying to merge this data here, these two data points here. Then we are going to merge here, right? And then we are going to merge here. And finally, we are going to merge here. This is your dendrogram. On the y-axis, we are going to plot the distances. On the x-axis, anyways, your data points are there. A, B, C, D, F. Now, in this case, I want to group this data, right? So what I can do is I can split it here. If I split it here, I will get two groups, two clusters. I have A as one cluster, this branch, and then the remaining B, C, D, E, F, all these belongs to one group. If I split my cluster here, then I would get 1, 2, 3 clusters. In this case, I will get 3 clusters. I'll have A as a separate cluster. Then I'll have B, C as separate cluster. And then I'll have D, E, F as separate cluster. Okay, so these are the 3 different clusters. Similarly, I'll try and probably group it here. Now I'll get 1, 2, 3, 4 clusters. So depending on what we are trying to achieve or what business areas we are working in, depending on that, we will be able to decide on how many clusters would be an ideal condition. It also, right, is a cost-based analysis that we have to do, because ultimately more the clusters you have, more strategies, more resources that you need to bring in. But the advantage is that within the cluster, there will be very, very strong similarity. Yeah, this is distance, right? Less the distance means more the similarity, isn't it? So I'll have more similarity if I talk about the right y-axis. Then here you will have more similarity. As and how we go up, the distances, similarity is reducing. That means there is more homogeneity. But as I said, the trade-off is that there will be too many groups, so too many resources to manage those groups. If you do not have too many resources, then you probably go up the ladder where homogeneity is reducing. The number of clusters is reducing, right? But within the cluster, there may be not such a high homogeneity, which probably otherwise obtained at the lower bands here. You can see, right? This is the distance between A and the rest of the records. Or if you talk about three clusters, A, B, C, and D, E, F, the distances are very far away compared to the distance between B and C, D, E, F, right? So these things. So this is the trade-off, but ultimately, depending on what we are trying to achieve, we are going to define the K value. The K value is nothing but the number of clusters. K is the number of clusters. So the hierarchical clustering algorithm is having two approaches. We will be discussing about agglomerative approach, which is based on merging. We will start with n clusters where each record is equals to one cluster. This is the assumption that we start with. N clusters. From here, we will try and do pairwise distances. Pairwise distances, we call it as multivariate distance. We'll measure multivariate distances. And we are going to here merge the most similar record. Whatever is the pair of records which are most closest, we merge them to create a cluster. We will keep repeating step 2 and 3 until we reach one single cluster. You repeat it until you reach single cluster. And this entire process is going to be visually represented in Dendrogram. And post that, we are going to decide the K value, which is the number of clusters. The advantage that we are going to get with respect to doing the clustering is that we will get homogeneous records, homogeneous pair of records. Now, once you have homogeneous, that means we will have consistency. With respect to the characteristics of the data, there is consistency. That means we will be able to have a certain value. That means we will be able to extract information easily. If there is uncertainty, inconsistency, then there will be difficulty in extracting the information. So this is the clustering logic. Now we will be using this logic probably in the next class, that is tomorrow's class. We will try and use a very, very classic and handy use case, which is performed on Starbucks. Right? We basically have the Starbucks data. It's publicly available. You can also try and use this example. On Starbucks data, we will be doing some geospatial analysis. right? So it's nothing but the data contains location details. And we're talking about branches of Starbucks. Okay, and we will be using libraries like GeoPandas, Shapely, Folium to try and visually deal with these branches on a map. OpenStreetMap OSM is something that we are going to use in our code. And again, these are all public code, so we should be able to very easily understand the code also. So we will be doing clustering, and we'll also be doing some additional work on that particular data. All right, so this is with respect to the clustering logic that we are going to implement on GIS data. So interesting session tomorrow. We will be using the clustering logic hands-on on the GIS data. So connect tomorrow to learn more. Looking forward to see you all. We will wind up today. Thank you so much for connecting. Hope you have enjoyed the session. Happy learning and take care, friends. Good evening, everyone.